Bennu is not heading for Earth, but JPL cannot rule out every future impact. It will probably miss. The question is what humanity does before then. This is Cosmion. Point it at any question in the universe, and it will show you the answer, whether you can bear it or not. So how can a safe flyby in 2135 decide whether Bennu can hit Earth generations later? Start with Bennu itself. OSIRIS-REx met a world of boulders. Bennu is about 490 meters wide, but it is not one solid rock. NASA describes it as a loosely bound rubble pile. JPL's model uses a mass of about 74 billion kilograms. That is a fitted mission value, not a direct weighing. Bennu turns once every 4.3 hours and completes an orbit of the Sun every 1.2 years. Mission imagery shows loose material and rocks filling the frame. Scientists watched Bennu rotate at close range and followed its motion. The future risk now belongs to a boulder-covered world they can measure. Now put sunlight on that surface. Bennu's terrain absorbs energy as it turns through daylight. Later, the warming ground releases infrared energy back into space. That release gives the asteroid a tiny push. JPL compared the force with the weight of 3 grapes. At any one moment, it is easy to dismiss, but the push returns as Bennu keeps rotating beneath the Sun. Across decades and centuries, the changes accumulate. This is the Yarkovsky effect. It does not throw Bennu onto a sudden course. It changes the orbit by a little, again and again, until a distant encounter shifts enough to matter. The force is tiny, but it acts for a long time. Ignore it, and the forecast slowly loses accuracy. OSIRIS-REx measured that thermal push in unusual detail. The mission followed Bennu from close range, letting repeated observations test the predicted path against the real one. Precision tracking reduced the uncertainty around Bennu's orbit. The spacecraft also descended to the surface, collected a sample, and backed away. That contact had a negligible effect on the asteroid's path. OSIRIS-REx touched Bennu, but it did not deflect it. The dramatic moment changed what scientists could study. It did not meaningfully change the impact likelihood. The useful change came through observation. Better tracking narrowed the range of possible paths through the encounter in 2135. NASA says those measurements ruled out a number of gravitational keyholes and removed several later impact scenarios. Nothing pushed Bennu into safety. The evidence simply left the model with fewer possible futures to carry forward. The decisive encounter is a safe one. On the 25th of September, 2135, Bennu is modeled to pass Earth at roughly half the Moon's distance. The nominal separation is about 204,000 kilometers, measured from Earth's center. Nothing hits Earth that day. Yet Bennu comes close enough for our planet's gravity to change its later orbit around the Sun. The flyby is safe. Where exactly Bennu arrives will determine how its path bends and how it returns decades later. A slightly different arrival point produces a slightly different departure. Over the following decades, those paths can bring Bennu back at different times and from different directions. That makes the safe flyby the hinge of the forecast. It does not send Bennu towards Earth. Earth's gravity sorts the possibilities into different departures. Most lead to future misses. A few preserve a later impact route. The name for one of those tiny regions is a gravitational keyhole. It is not a hole in space. It is a narrow part of the encounter geometry in 2135. If Bennu crosses one at the required time, Earth's gravity would send it onto a later orbit that returns to Earth. Miss that region, and that particular impact route disappears. The keyhole does not pull Bennu in. It marks the arrival that Earth's gravity would transform into that later return. Current models have not removed every route. In 2135, a difference that looks small on the way in can select a very different path on the way out. The miss remains overwhelmingly likely. So which surviving path carries the largest risk? JPL's answer points to one date, the 24th of September 2182. For that single encounter, the live model gives Bennu about a 1 in 2700 chance of impact. A miss remains overwhelmingly more likely. This is not a forecast that Bennu will hit. It is the largest probability attached to any one retained date after the orbit was narrowed. The model has moved from a broad range of possible futures to a smaller set of routes with measured odds. The number describes uncertainty. It does not schedule a collision. A second figure sits beside it. About 1 in 1750. It sounds larger because it answers a different question. 1 in 2700 belongs only to the 24th of September, 2182. 1 in 1750 is cumulative. It covers every retained impact possibility through 2300. It does not increase the odds for that single day. The cumulative number is larger because it gathers several dates into one span. It does not make the 2182 encounter more likely. Each figure keeps its own time label because each measures a different slice of the future. One asks, what is the chance on this date? The other asks, what is the chance across every retained date in this span? Both are small. Both can change as observations improve. Neither describes a current collision course, so why spend generations measuring a risk that will probably never happen? Because even a small chance can matter when the consequence is serious. If Bennu hit, JPL's model uses an impact speed of 12.68 kilometers per second and about 1.4 gigatons of energy. Those are conditional values, not Bennu's present motion towards Earth. NASA does not publish a Bennu-specific casualty count, crater, tsunami, or climate forecast. Its generic scale brackets Bennu between a smaller regional reference and a 1-kilometer global reference. It does not turn those reference points into a Bennu prediction. Taken together, Bennu's size and modeled energy support one careful conclusion. An impact could cause severe regional devastation. It could not destroy Earth. The chance is small, but the consequence is serious enough to justify patient measurement, while the safe encounter is still generations away. Patient measurement is humanity's real advantage. Bennu's heat keeps adding a tiny push. Across years, that accumulated push shifts when Bennu reaches the safe flyby. Then, during the flyby, Earth's gravity changes the orbit Bennu takes away. That departure orbit determines which later returns are possible. This is how a safe flyby in 2135 can decide whether a route to Earth remains open generations later. A small shift before arrival can become a different future after departure. Future observations can keep testing the routes that remain before Bennu reaches that encounter. If a credible impact route survives, humanity would have time to decide whether intervention is needed. If observations remove it, that route would need no response. The work now is to learn which future is real. That is the advantage. We can measure the arrival timing for generations before any response might be needed. Time is not merely delay. Here it is evidence, gathered early enough to turn uncertainty into a decision. Subscribe. Next, we enter NASA's rehearsal. For the day an asteroid warning stops being distant.